Hi class, and welcome to week 5. This week we're going to be focusing on volcanoes, and obviously that leads right into igneous rocks. It's a good place to jump to first from plate tectonics in terms of, igneous rock is only really one of 3 basic types of rocks. We've got igneous rocks, we've got sedimentary rocks, and then we've got metamorphic rocks. And we're going to be going over sedimentary next week. We won't be getting into metamorphic rocks, even though they are really cool. Igneous and sedimentary are going to be the primary ones that you're going to see in our region. I may add a little bit of something briefly about metamorphic rocks, but it's a big subject to get into. So just a few logistical things first. We've got the videos, just like every week. With the homework, there isn't actually going to be a start here for this particular one. It should be relatively straightforward. This handout here is going to have some information about how the different types, the different shapes of volcanoes end up getting created. I'll talk about it a bit later, but my biggest hint there with volcanoes is that viscosity is really key. How that magma flows really goes into how each volcano shapes itself. And then, of course, when you are ready to submit your homework, you'll take a look at these questions to answer, and then in the quiz here, you'll end up answering those questions. So just take a look at those. And yeah, it looks like I'm still on teacher mode, so you can see all my hidden stuff here. Not a big deal, but anyway. Under the labs here, we're going to start on igneous identification. And identifying igneous rocks can be a little complicated, and I'm not quite so happy with the way that the videos here go over some of this information. They kind of talk about things out of order, and so I'm going to create hopefully it won't be too long, but the later part of this video is going to be a little sort of lecture for trying to get some of those ideas into scope before you watch those videos, or even afterwards, to hopefully kind of bring all that together in context so you can kind of understand the gist of everything. So if you I guess from here on out, that's what I'm going to do. I'm going to do a little lecture thing. You could stop watching because it might be kind of long, but I think it'll be really helpful for you, whether you've seen the videos or not, because you might end up watching the videos and saying, actually, I might want to look at that. So, okay, so let's start talking about, well, first off, let's talk about the rock cycle. So the rock cycle is sort of a general term that we end up using to describe how these 3 main types of rocks can sort of interchange or transform from one type to another. So first off, let's talk about igneous rock. Igneous rock is formed when molten rock cools and solidifies. But igneous rock can turn into sedimentary rock if we weather it and break it down. You see over here, if you take igneous rock, weather it, and then you can turn it into sedimentary rock, which is formed from the fragments, the small little bits of whatever rock you're breaking down. Now, the rock cycle is kind of interesting because you can get sedimentary rock from metamorphic rock, or you can even get sedimentary rock that was made from previously constructed sedimentary rock. And metamorphic rock is when you take really either any of these rock types and you squish it with pressure, and you subject it to great temperatures, and you warp or change that rock. It's kind of like if you were to bake something, and squish it while it's baking. It transforms some of those minerals from one type into another. So metamorphic rock can be actually pretty complex, and we're not going to get too deep into it in this particular course. But let's move on. So the videos are talking a lot about these terms that I'll go into in a little bit, mafic and felsic. And it really plays an important role in the understanding of igneous rocks in general, and even just plate tectonics, because they've been kind of just going over and talking about, that continental crust is more buoyant and oceanic crust is more dense, and these things are actually really important factors in pretty much the entire Earth system. And so why is oceanic crust more dense? Why is continental crust less dense, lighter? That's kind of what I hope to go into here, is that, and they even talk about in the early eons of Earth how the composition of the rocks and things were different, but they don't really go too far into what significance that has. Well, the significance is that when you melt rock and then you allow it to cool slowly, it can change from one type of composition to the next. And so when we have liquid hot magma, we end up cooling it slowly, some of the melt, let's call it mafic, it starts off mafic. And mafic comes from these minerals, magnesium and iron, or ferrous, Fe, right? Mafic means that it's got more of those heavy elements in it. And at those higher temperatures, those crystals, minerals with those sorts of elements, those heavier elements, will form first and settle out in that melt, like sand falling through water, right? They'll settle at the bottom of the magma chamber, which leaves the rest of the melt depleted in some of those heavier elements, the iron, magnesium, calcium. And so it moves from a more mafic composition. Again, mafic and felsic are descriptors of elemental composition, what kind of elements are in there, and moves from mafic to felsic, so from more dense to less dense. And we're still talking about molten rock here. And as it moves its way up through the crust, this process continues to happen, and it cools more and more, other kinds of minerals start falling out. And that remaining melt becomes enriched in some of those lighter elements like silicon, aluminum, sodium, and potassium. And this is kind of what we're talking about when we talk about the evolution of magma, or magma types, which of course is really important in volcanism and how those volcanoes end up shaping themselves. But let's take a look again at this here. So we got melting as this downgoing slab gets heated. Some of the water that was chemically bound in the minerals of this oceanic crust, when it gets to this heat, this depth, with this pressure and temperature, that water actually comes out of the rock because those minerals change from one type of mineral to another. They release that water, boom, just immediately. When that water hits that rock, even though it's the same temperature as the surrounding rock, just that little bit of water caused the melting point of that magma to be lowered, and therefore, boom, you get melting rock. That melting rock, even though it's the same temperature at that point, it's going to start rising because it's now less dense, it's more buoyant. And it starts moving its way up through the continental lithosphere and through the crust. And as it does so, it starts differentiating. It starts dropping out the heavier elements, leaving it enriched in light, until it gets up into the continental crust. Some of those magma chambers will solidify underground without ever reaching the surface. And that's actually how we get continental crust, period. Like, this process has been going on for billions of years. And so the more this happens, the more melt differentiates, the lighter the material gets. And of course, when you start putting this melt up into the continental crust, some of the continental crust will break off and dissolve, melt into that magma chamber, which will enrich it, right? And that process generally, over a period of time, causes the continental crust to become even lighter. It's a very fascinating process. And this is precisely why we have stratovolcanoes, whereas Mars does not. It's because on Mars, the magma never gets to this evolved state where it's got extra silicon and aluminum, sodium. The lighter elements actually cause the magma to be stickier. We'll go into that in a second. But it's because of that that we have these big, large stratovolcanoes. So the videos talk about Bowen's reaction series. And there's a lot of information on here you don't need to know, but they confuse, I assume, the video is a little confusing with the discontinuous series and the continuous series, and the minerals they're talking about. This is basically just saying that as magma goes from higher temperature to lower temperature, these are the minerals that I was talking about, the mafic minerals that end up forming first as that melt is really hot. The discontinuous series just means that these are different minerals that end up forming at different temperatures. The continuous series just means that it's actually the same mineral, but with different concentrations of sodium and calcium. So, not that you necessarily need to know this stuff, but that is essentially what we're talking about when we say that a rock will go from mafic to granitic or felsic, as we also say it. We also say that it might go from basaltic composition to granitic. Okay, so the video briefly talks about extrusive and intrusive settings for volcanism. And it's pretty simple, really. Extrusive or volcanic is when magma gets extruded out onto the surface, sometimes blown into the air. And intrusive is when that magma doesn't quite make it to the surface and cools at depth. And these two igneous environments are important because, with extrusive, or at least pretty close to the surface, that magma cools rapidly. And so it chills too fast for larger crystals to grow. So it almost looks fine-grained, like almost like a sandstone sometimes, or if the material is close enough to the surface and it doesn't have much pressure on it, the dissolved gases in it can kind of froth it up like pumice. You know, pumice is an extrusive rock. And with intrusive, you cool that magma really slowly, and so you will usually get larger crystals. Sometimes they can get quite large, especially if there's a little bit of water in the mix. And so the key thing to understand here is that you can have magma that is of one type of composition, and yet you can get rocks that look very different depending on how quickly they cooled. You could get what would be called a rhyolite, rhyolitic composition. It's kind of the more felsic end, so plenty of silica, lighter elements, and things like that. And rhyolite, when it ends up on the surface, can look like this pink, almost sandstone-like rock. Whereas if that same rock were to cool slowly underground, it would look more like a granite. So that's the key that I'm trying to get across here, is that composition can be the same, but the rocks can look quite different depending on how quickly they cooled. So let's move on. And for those of you that are working on the labs, you might find this pretty helpful. So when we're talking about how rapidly they cool, we call that texture, or rather, texture is created based on how rapidly they cool. For example, here I was talking about rhyolite and how it can be this like fine-grained pink stuff, and sometimes it'll have larger crystals in it from when it was maybe close to the surface, and some of those crystals started to form, and then it erupted, and so the rest of the material cooled really quickly compared to those other crystals, so they get locked in there. That's a different kind of texture. And granite is going to have some of that same pink, but definitely looks different, right? The minerals that are present really do depend on the composition and not how quickly they cooled or whatnot. And then the color, of course, is one of the primary indicators that we use with igneous rocks to determine whether they're more mafic or felsic, right? More mafic you'll tend to have these darker crystals or green as well. And those are going to be on the mafic end, and then you move into the intermediate, and that tends to be sort of gray overall. And then in the felsic end, you end up usually getting a lot more of this pink in there. Again, some of these charts are more just for your understanding, not necessarily that you need to know these things. So this is kind of just another way to look at Bowen's reaction series, or what I was just showing you with igneous compositions. Over here we have the mafic end of things, and we move towards the felsic end of things. And this is just showing you sort of percentage of like what types of minerals you might find. Whoop, food's done. What kind of minerals you might find in that particular rock. But this is just to kind of put it on a scale for you, right? The more towards the left you go, the more felsic it is, the more silica rich it is with sodium, potassium. The more mafic it is, the more iron, magnesium, calcium there is. And the darker those minerals are. And then felsic, of course, is on the lighter end. And this also shows intrusive versus extrusive, the names that we would use for that. So like a felsic rock that is, we would say maybe granitic or rhyolitic in composition, would have a different texture and thus a different rock name depending on how it cooled. And once again, I bring this up because next we're going to look at volcanoes, and I wanted to just point out that with an increase in silica here, So the more felsic we get, the stickier that magma is going to get. And also, the other factor, of course, with viscosity is heat. So when I think about viscosity, I tend to think about honey. Viscosity is how easily something flows. So cool or room temperature honey flows kind of slowly, right? But if you heat it up, it flows very rapidly, right? So temperature is one big factor in what kind of lava flow you get and what kind of volcano you end up getting. And so, as it's shown here, basaltic lavas, they tend to be hotter because they haven't traveled through as much crust to get to the surface. And they tend to be more mafic because of that. And so because they have less silica, because they haven't evolved as a magma much, there hasn't been much differentiation, and it's hotter, that's when you see those big basaltic magma flows coming out of like a shield volcano like in Hawaii. And the more towards a continental volcano you get, like Mount Rainier, Mount Hood, the more evolved that magma is. The longer it's had to go through the crust, the more cool it's become, the less heavy minerals it has, the more silica it has, and because of that, it's thicker and stickier, and so it tends to block up or not flow as far, and that's when you will sometimes see those lava flows that are just full of broken pieces, right? And that builds a steeper volcano. So hopefully this information is helping you with all this. And I'm not going to belabor it anymore. You should have plenty of other stuff to cover. So hopefully this helped.